Hello, everyone. Hi, good morning, good day, good afternoon, wherever you are. Thank you for joining the Geoscience and Geoenergy webinar of 27th of January 2021. Today, we have the pleasure and honor to host Professor Jan Main from the University of Edinburgh. Jan is Professor of Seismology and Rock Physics at the School of Geosciences at the University of Edinburgh. And he has a BSc, Bachelor of Science in Physics from the University of St. Andrews, and a PhD in Seismology from the University of Edinburgh, where he works today. Jan works on the processes that lead up to catastrophic failure events, from laboratory rock failure to volcanic eruptions and earthquakes, as well as the failure of engineering structures, and in quantifying the resulting hazard. He has particular interests in the statistical mechanics and population dynamics of localized brittle failure as a complex, multi-scale, nonlinear system, as well as the influence of old, new, and reactivated faults and fault zones on fluid flow underground and on the risk of induced seismicity. Quite a very high and highly important and impactful topic in many societies today. Jan moderated the 1999 Nature website debate on earthquake prediction and acted as an invited member of the International Commission for Earthquake Forecasting for Civil Protection in the wake of the 2009 earthquake in Italy. He was awarded the Louis Nagel Medal of the EGU at the European Union of Geosciences in 2014, and the Ed Lawrence Lecture in Nonlinear Geophysics at the American Geophysical Union AGU in 2019. It's a true pleasure and honor, Jan, to host you today. Thank you for graciously accepting our invitation. To the audience, please note Jan's lecture would last for about half an hour, followed by discussions. And like always, please do type your questions in the chat box. And at the end, Andreas Bush is here with us. I forgot to introduce him at the beginning. Andreas is here because Sebastian couldn't make it, but you have seen Andreas before in many occasions. So Andreas will chair the discussion session today and pick up the questions, and we will look forward to having a lively discussion session as well. So without any further ado, Jan, the stage, the bandwidth is all yours, and we are all very much looking forward to hearing your lecture.
Okay, thank you. I'll just share.
Yes, please. You are sharing your screen. Yes.
Yeah. Okay, I see it.
Click on your file, then I can bring it. Yes.
That's it. Does that work?
Excellent. Yeah, please.
Okay, well, good afternoon, morning, or evening, depending on where you're dialing in from. It's very nice to have this opportunity to share some of our recent results from the laboratory at the School of Geosciences. So I'll be looking at the processes that lead up to catastrophic failure. That is before there is a fault in this rock sample here. You can see there's a nice shear band developing. And that occurs because of the complexity of the material, the various potential nucleation sites, fractures in the shear that can occur on these weak points, if you like, and they can eventually connect up to make a fault. And just very recently, we've been able to image this with high-resolution synchrotron imaging. And you can see the kind of possible resolution here in terms of a sandstone in this case. It means that we have to have quite a small sample, though that's the downside at present. So most of the results I'll be talking about are on relatively small samples, but still a representative number of particles for a complex system, porous medium. And then from looking at the particle tracking as from time-lapse images done in the synchrotron under stress, in these live deformation experiments, we can back out the incremental strain between time-lapse images and therefore get an idea of how this deformation is resulting in local strain. And I'd like to say as well, while I'm on the title slide, that this is I'm presenting as a tribune, really, the results of this large group of people who have been either involved in the experimental design, the experiments, the analysis of the results, or in their interpretation. So that this is a large body of work, really, that I'm summarizing very briefly here. So this is the potential that's been opened up by the synchrotron. We can get our sample, put it in the rig. We designed a new rig to be able to do this. And we increase the stress in steps, and then we have to hold the stress constant, hold the conditions constant while we take the image. We don't want there to be too much deformation while we're taking the image. And then eventually we see the fault beginning to, the shear zone beginning to form here, and then catastrophic failure of the sample at some point. The first set of experiments, we looked at an intact piece of Ailsa Craig microgranite, which is an amazing material. It has, as you can see, almost no cracks. It's one of the few materials in the world with so few cracks in the natural material. The island does have some joints, but on a microscopic scale, it's really just equant pores that you can see here. So very low porosity and very low permeability material, pristine. And then we analyze the samples during after the run. So during the run, we'll take all the CT data, then we'll make the tomogram, and then we need to segment the image. So we need to pick out the cracks as these blue areas where the porosity has gone to zero effectively. And it wasn't before. And so this is in 3 dimension, and this is a 2D slice, which tends to emphasize the bigger cracks. If you take a slice, you miss a lot of the small ones in the volume. And these are the resolutions. A pixel size of about 3 microns, and an actual resolution when you do the segmentation to pick out the new cracks of about 14 microns. So that our the total porosity we get from the segmentation is always a bit less than the actual total porosity of the sample. And then, of course, we've got all these cracks, which are in general fractal objects, so sort of kind of rough. But to get statistics based on a kind of a representative dimension, we fit a best fit ellipsoid to this, and we measure the lengths of the major, minor, and intermediate axes, and they give us length, width, and thickness of the crack. And it also defines a centroid, and that is, if you like, it's like the epicenter, the centroid of the earthquake, the center of the deformation. And that gives us a kind of location for the crack, a representative location. And we can also, from the two lengths on the ellipse, we can get the associated aspect ratio, and then we can get the intercrack spacing from the distance between the centroids. And so when we squash a rock, we find that we see at the onset of, this is differential stress against strain here, at the onset of yield, we begin to see a softening of the material. And this occurs more markedly in the sample where we've put in some disorder. In other words, we heat treated the sample, which started off with no cracks, and we put some cracks in deliberately to see what effect having some damage in the prior material was, in a controlled way, so we could control the amount of damage in the starting material. And we see that it yields at a greater extent. And you can also look at the evolution of the porosity in the heat-treated sample. You see it's more stable, and then it begins to accelerate, a lot of damage accumulating towards the failure time. And in the untreated sample, we see much more porosity increase because it started with no cracks, so it's less compliant in a way, and you have to put in more cracks to provide the strain. We can do statistics on the number of voids, which also show this nonlinear acceleration. And here's the exponents. They're very high, 3.08 or 7.66, 8, 3. These are big numbers for nonlinearity. You know, that's consistent with the brittle behavior of the material eventually. We see emergent power law scaling. So this is the cumulative probability distribution for crack volume. See a nice power law, a straight line on these plots. We see it starts off being random nucleation of cracks, which is an exponential distribution. And for the untreated sample, the one that started with no cracks, the absence of damage means there's fewer stopping places for the cracks. So you get this bulge here, which Didier Sornet calls the Dragon King. There's more cracks than you'd expect, more big events than you'd expect by linear extrapolation from the smaller ones. When you do the heat-treated samples, we provide these kind of stopping points, and you get just a smooth power law distribution all the way up to the biggest events. It's like a pure fractal, really. And the same is true for the distance between events. We see its probability density distribution is also power law, and the slope of that defines the correlation dimension, the degree of clustering in a self-similar way of the probability distribution for the intercrack distance from the centroids of the ellipses. So we already see that the properties of the starting material have a big effect on the outcomes. The number of cracks in your starting sample will affect, you know, the actual size distribution that you get subsequently. We see changes in crack shape. We see no change in the mean aperture, but we do see increases in the crack width and the crack length, even more so. And the same for the heat-treated sample, which starts out with more cracks in the beginning. So that means that the crack growth is not self-similar. Okay, it's getting longer and flatter with strain post-yield. Okay, so the cracks are becoming longer, but they're not really changing their aperture very much. And this has got implications for interpreting things like seismic anisotropy, which often assumes a constant aspect ratio. So the aspect ratio is changing when we do the tests. Okay, so now we're going to look at sound and vision, and this is acknowledging a contribution here from David Bowie's album. As far as we're aware, these are the first tests to combine the acoustic emission monitoring of samples undergoing this kind of deformation. So this is a new test now on a sandstone sample, not the granite, where we had no acoustic monitoring. What we see is the development of the shear band, and we can now listen to hear what sound is being emitted from these cracks as they develop. And we can also look at the incremental strain in between snapshots, which picks out the difference in position between, say, a feature of a green grain boundary or a void or something like that. So we do digital image correlation to infer the strain. So if we go back to the literature, a while ago, David Lochner and his group, 30 years ago now, discovered that from acoustic emission monitoring that initially cracks, acoustic emission sources, microseismicity, occurs randomly in the sample, and then it begins to localize. You can see the shear localizing here, and then that little shear band grows further and further until it crosses the sample. So you get this cloud of seismicity centered on the eventual fault plane. And this hadn't been seen before, this seminal paper. And the reason they saw it at all is because they backed off the strain. They used the acoustic emission event rate to back off the strain under servo control, and therefore take the sample down this stress drop phase in a stable way. And so that gave this beautiful image of how a shear crack is growing as evidenced by the acoustic emissions indirectly. So now we've got the capability of combining this with synchrotron imaging to see if this is actually, what the meaning of that is. And so here's our sample. This is just a standard constant strain rate test, which fails dynamically with no feedback control other than the constant strain rate loading. And then all of this stuff happens here. So we don't normally see it under the conventional testing protocol. So here are our images in the granite specimen, and we didn't see what was happening at peak stress. But we did see a fault plane eventually. We just didn't see how it went from all these little tensile features here aligned with the sample axis. How did it go from here to here? So this is what we've been able to do with the servo control in the more recent tests. And this has the sample in here and transducers top and bottom. So we can listen to the sound. And then there's a sample going in there. And then these were presented first by Alexis Cartwright-Taylor and Maria Daphne Mangrotis last year. And we're working on writing this up at the moment. It's in review. So here's the sample, and now we can combine these two. And with the feedback control to look at this data gap. So there's what happened. In the dynamic test, the constant strain rate loading, everything just goes bang at one point. And in the feedback control, we've got this extended phase of strain softening associated with all these different stages, which are happening in an instant in a normal test. So we can stretch out the time scale and see what might be happening to cause the fault to localize and grow. And here's a picture of the feedback control working. So if you have no feedback control, you just see the inverse power law acceleration in event rate. If you do, then you have there's quite a bit of dither, which is quite standard actually in feedback control, hopping slightly back and forth, but it's feeding back on an event rate of about 1 event per second. And you can actually pick this up at Research Square on open source at the moment while it's in review. Okay, so I've spoken about that. And so we essentially have reproduced the protocol of Dave Lochner and his group. So this is their results in the Nature paper. This is ours in one of the tests. And now I'm going to walk through what happens as you go over this curve. Do you see that? It's difficult because I can't hear you. But we were so excited when we got these results.
We do see that, Jan. Sorry, it took a minute until I could unmute myself. Yeah, absolutely.
But, I've been working on this a long time using acoustic monitoring, but it was just a joy to be able to see what this meant. When you see the fault, the shear zone, sorry, it's not a fault yet, just occurring kind of spontaneously, and how quickly it's already self-organized into a shear band. Yeah? This is a bit different from what we saw with the acoustic emission data. It looked like there was a nucleation and then it grew, and we'll show that that is correct. But there's also this very long shear zone, which is there all the time, which the acoustic emissions were not necessarily picking up. So I'm gonna, you can see that the strain softening is associated with this coherent shear across the band here. This zone is breaking, is being damaged more at kind of peak stress, and then it goes into this organized failure here. So I'm going to walk through one by one. It's like a slideshow. And we're going to look at specific features in the starting material. And you see how quickly everything self-organizes along the shear band. Okay, the previous time step to now. Your eye is very good at seeing correlations.
Yeah, indeed, yes.
And then you can see that, initially you've got these tensile cracks, you've got some shear on the grain boundaries, and you've got a bit of rotation. The grains are rotating to enable coherent slip to occur. And the intact rock is staying pretty much where it is. There's not much damage outside the shear band once you get localization. And then in some cases, it even over-rotates. So now you have this fracture is now shearing in the conjugate direction. Okay, so everything else is shearing in this sense. And now this one is shearing in the opposite sense because it's over-rotated in the field. And then you can also see that there's no fault. It's just a shear zone of deformation. And there's a mixture of tensile and shear deformation associated with microcracks and sliding along grain boundaries. And rotation is really one of the big processes accommodating the movement of the top hanging wall over this footwall here. So I think I've said all of this. But eventually, coherent slip occurs in a contiguous fault plane. Eventually, you do get a breakthrough, and there really are two bits which are not in contact. Just one last time. Yeah. So these are now the digital image correlations showing the strain. Starts off with no strain. So it's all black, and then you start to see a low amount of strain. Here's the key here. This is a shear strain as an example. And then you can see it's, by the time you get yield, you're starting to see localization. You still got this random deformation that was inferred from the AE and Dave Lochner's experiments. And now you're starting to get more localization as you get to peak stress. These are 3 different time snaps near the top. And then you start to get movement on the shear band that's actually going to form the fault plane. So these are candidate shear bands, which never made it. It picks one optimal one for some reason, and then it stays there. And you see this nucleation and growth of the band where the strain is very high. And then this is the peak strain at the, almost the steepest slope here when the stress is dropping. And then once you get stable sliding, you see there's a relaxation of the incremental strain. It's a kind of elastic rebound because now the fault has formed and there's no drag, or not so much drag across the 2 sides. So you get a kind of strain relaxation. Not unlike the idea of elastic rebound for earthquake mechanics, except that all of this is quasi-static. So now I'm going to take these snapshots just after peak stress, and they compare beautifully with the 1991 paper results just from the acoustic emissions. I'll just leave that with you for a moment. This is to me, this was a significant result. We could actually reproduce what the acoustic emissions were showing, and that gives you an idea that actually it is a sensible thing to make inferences from acoustic emissions, and that actually they are capturing, pretty much the most important things in this example. This is not like for like. We haven't got locations to this of this number of locations because we're using such a small sample, but it shows a nice correlation. The acoustic emissions themselves, this is just the usual. We measure the maximum amplitude as a function of time, and these are all the data points, and then from that you can work out the frequency of events. It's kind of constant, plus or minus quite a bit of scatter in the feedback control. The frequency magnitude distribution gives us a relatively steep slope, just under 2. It's not completely atypical of induced seismicity, actually. To have a normally for earthquake seismicity, this is around about 1. And another thing we can do is count up the amount of deformation from the inferred seismic moment. and compare that with the total strain that you would expect in this from the bulk deformation. And we get a very small ratio of the seismic moment to what you'd expect given the strain that you observe on the sample. So it's less than 2%, depending on where you pick this threshold or how far you extrapolate it back. And that means that the strain is primarily aseismic. So all these stable shear, the rotation, they seem to be dominating the actual strain in this case. So the acoustic emissions are only really recording a tiny proportion of what's going on in this case. In fact, this proportion of seismic to aseismic deformation is one of the biggest known unknowns in induced seismicity problems. Before you start, you don't always know what that's going to be. It can be near 1, or it can be 10 to the minus 5 or something like that. So 10 to the minus 2 is not atypical for induced seismicity settings. Another thing we noticed about feedback control is that it suppresses the large magnitude events. So here's the dynamic loading experiment, the one that's normally done. Here's the one with feedback control, which gives us this quasi-static strain softening. The dynamic experiment gives us a lot more big events. Okay, so the feedback control, which kicks in about here on this vertical dashed line, is suppressing large events. There's a slight difference in the threshold, the magnitude thresholds here. They're recalibrated to the same scale, but we used a higher gain, sorry, on the quasi-static loading, because we did this test after the dynamic loading test. So we'd learned we could get away with a higher preamp gain. And then you get, I've already shown this inverse power law acceleration and the fact that we deliberately slowed it down to a constant strain rate here. So what this means is that maybe if you want to suppress big events, the way to do it is maybe not to record the big events on their own, like you would have to do for, say, a traffic light system. Maybe the best thing to do is actually to feedback on the event rate. And that's something for discussion, in terms of how one might manage the risk of an induced seismicity setting. We've done some work on the locations as well. We've got a big problem in that we've only got 2 sensors on the top and the bottom of this sample, but we can still do quite a lot with that. We can't put sensors on the side because then we wouldn't see the resolution that we need with the CT images. We couldn't get X-rays in as easily. So we really have to have X-ray transparent cell walls. So we're limited to 2 sensors. So all we can do really is map out a whole load of possible positions as a kind of bowl here from the 2 travel time measured above and below the sample. But we also have the information from the strain, so we can pick the most likely location as the intersection of this bowl with the area of high strain. So we kind of use the strain field as a prior, a strong prior. So we put the event there. And so you can see there's few events, and then you start to get more, these red dots. Some of them are on the shear plane, and some are still off it. There's quite a few big events off the shear band, which I'll come to later. You begin to see some localization here of the acoustic emissions. So we don't have as many data points to compare as the Nature paper by Dave Lochner's group, because we've got a smaller sample, so we've got fewer acoustic emissions. But we can back out some inferences from this. We find that there's a strong correlation between the volumetric and the deviatoric strain, or the dilatant and the shear strain. And that's because we've got this mixture of tensile cracking and shear right on the shear band. So also dilatancy makes it easier to shear something past another rough object. So it's maybe not surprising that there's a high correlation. And this is the acoustic emission amplitude plotted here. And what we find is that only a small fraction of acoustic emissions occurs in locations where the strain is recorded. We've got strong correlation between tensile and shear strain for events with an acoustic emission location. And we've got minimal acoustic emission for compaction events. No strong correlation between acoustic emission amplitude and local strain. So these kind of confirm our inference from the summing up the seismic moments that the strain is predominantly aseismic. And this was a kind of surprising result. We find that the acoustic emission amplitude is highest in areas of low strain. Okay, so there's a sort of negative correlation between the strain and the acoustic emission amplitude. This is kind of a surprise, but it's maybe not surprising given that we see so much evidence of aseismic deformation on the shear band. It's also a result which is expected from a fiber bundle model for avalanches in a more generic sense, which was published recently. But this does have implications for our inferring properties of the deformation from just looking at the seismicity alone. Okay, so quite a lot of conclusions. We've got emergent power laws in the evolution of damage. That's the number of events and the volume of crack population, frequency, volume, and frequency spacing distributions. The cracks grow longer and wider, not fatter. That means we're going to have changing anisotropy. We see weakening by self-organized localization of the deformation on a shear band, and that happens very coherently, very quickly once you go over peak stress. And the shear band strain occurs by nucleation and rotation of on echelon tensile microcracks and local slip at the grain scale. The system doesn't know where the fault is going to be right away. It tries out some candidate fault orientations before it picks the optimal one, or the one it's going to be in the end. We see this intrinsic correlation between shear and dilatant strain that you can see on the image. You can see the tensile cracks associated with shear. And then there's a large fraction of aseismic deformation in the shear band. And the largest seismic events tend to occur in areas of low strain out here in the bulk, where it's still brittle. And finally, the large magnitude events can be suppressed by feedback control on the acoustic emission event rate. Okay, thank you.
Thank you very much.
I'll leave the conclusions for a bit.
Yes, thank you very much for this extremely interesting and fascinating talk. As you said, also, we could pretty well actually detect all these kind of relative motions at that grain scale, which is quite nice. So I'm going to try to remove your screen from the show, and we have plenty questions already posted. I would expect more will come. So we could ask you also dozens of questions, but our audience have their priority. So Andreas,
understood.
Andreas, please take it from here. And
just a second, I'll let the cat out.
We have also another unexpected audience.
Yeah. Fortunately, my dog is sleeping, and I'm having the headphones. Otherwise, you could have heard the cat.
I believe your cat has a question too, Jan, but that's okay. So, Andreas, please, that was nice.
Yeah, no, thanks, Ian. That was a great talk. That I heard about these experiments, but I haven't actually seen a presentation about the experiments. So that was fantastic to see. So I think we go chronologically, and when we do that, we would start with Auke Barnhorn, and he's asking or saying, first of all, I understand fractures become longer with increasing strain, but why do they become flatter during deformation?
That's maybe not. That's maybe not a good way of putting it. You're right. They don't really become flatter. They just stay the same width. Not width, thickness. So length and width.
Aperture.
Width is the intermediate axis, and then the shortest axis is the thickness. But no, that wasn't a good phrasing. I need to edit that on the slide.
I see.
They seem flatter. If you don't have a scale, they seem flatter, but they're not really. They're just the same flatness.
Okay, there's another question from Yuhang Wang. Hi Ian, fascinating studies. What is the physics or the mechanism behind this non-self-similar propagation of the cracks?
That's really a good question. I mean, we've seen a few things where the kind of simple fractal kind of explanation wouldn't work. My feeling is it's something to do with the confining pressure. I think it would be interesting to do the experiments with a range of confining pressures to see if the aspect ratio is improved. Does have more scale invariant growth. It does. So it's not what I said was it's not self-similar. It may be self-affine. Okay, so you can have fractal systems where, like topography, where it's not a self-similar fractal because it's got different scales on the x and the y axes. So it could be that it's still self-affine. We haven't actually checked that. And there's lots of natural systems which have self-affine scaling that can be explained by simple cellular automaton models and so on. For example, in the topography for erosion, depending on the local slope. So I've no doubt that you could come up with a possible explanation for self-affine scaling, and we haven't actually tested that.
Yeah, excellent. The next question is by Barnaby Fryer, asking, how do you marry the acoustic emission observations where you see nucleation and the propagation rupture to the near instantaneous formation of the shear zone with this imaging? Is this just a question or a solution?
Yeah, I think the acoustic emissions, especially when you've got the servo control and so on, and synchrotron is a noisy environment. So our magnitude threshold is pretty high. I'd be more comfortable if it was lower. But this is an optimization problem here, and this is the optimal we could do to maintain the image resolution with acoustic monitoring. And as these sources, the light sources, the X-ray sources get stronger, we'll be able to use bigger samples, and then maybe we'll have more, a better resolution of what's going on. But yeah, it does seem surprising that you have a coherent shear band growing, but all the same, very quickly, but all the same that there are zones within that which start small, where there's very high deformation within the shear band, and then they grow. So you still get a picture that is similar to that found in the early experiments by Dave Lochner's group. But it's not telling the whole story. It's missing the aseismic component of the deformation. And that's what we've been able to do in our study, is to put those things together and highlight the importance of aseismic deformation, as well as the fact that the acoustic emissions alone tell you a lot.
What is, probably I missed that, Ian, what is the size of the samples that you used? That's a couple of millimeters in diameter, right?
Yeah, it's about three. I think it was about, the second set of tests, I think, is about 5 millimeters diameter. Okay. I would have to check.
Yeah, the other one was 10 millimeters, the one that we observed the shear band.
Yeah.
Okay, so that shear band width is on the order of a couple of 100 microns, maybe. Something like that.
Yes, it's the biggest crack is about 2 grain diameters. And that's roughly the size of the shear band. We don't get much propagation beyond that.
Yeah. No, good.
In these experiments, you might, in other experiments, different confining pressures with fluids or whatever, you might see different results, but that's what we've seen so far. It's relatively narrow band, and it's controlled primarily by the grain size.
Fascinating. There's a bit of a discussion between Yuan Wang and Barnaby Fryer. So Yuan was asking if there's numerical studies which can capture these physical observations. And Barnaby is answering that partly. I don't know. Maybe you just want to follow on with Yuan.
I wouldn't be surprised if there aren't. I mean, the most obvious one is the discrete element simulations. I've been involved a bit in, with a group in Hungary who do this, and then more modern versions which include the angularity of grains, and you can almost dial in the actual shape of your grain structure in principle. So the computation is certainly getting much better at doing this, and I wouldn't be surprised if in time that there's a good model which can reproduce this if it hasn't already occurred. But clearly, there's an interaction between the theory and the modeling and the observations, and sometimes one leads the other, and other times it's the other way around. But I'm not aware of any, theoretical studies that capture all of this at the moment.
No, it's probably.
It doesn't mean they don't exist, but.
Yeah. There's a question from Alex Novikov, also thanking you for the excellent talk. There's quite a novel approach to characterize porous geometry for micro-CT with the help of Minkowski functionals.
Okay.
Just in case you heard about it, do you think it may be applied for the analysis of failure in porous materials? So that probably requires that you have heard about it.
Yes, it's the first time I just wrote it down, but so thanks for the suggestion. There's a lot of different ways of analyzing this kind of data, and we are to some extent investigating different, ways of doing it, which might have a better resolution or different advantages for different applications. So we're very open to kind of post analysis of the data in future projects. So I will have a look. Thank you.
Good. Yuan Wang is asking another question. Has there been benchmarking studies to reproduce these results, probably with modeling and simulation?
I don't think so. I mean, it would be good to agree a bench. I mean, all numerical modeling studies normally have some sort of benchmark. So people doing software in different parts of the world can compare the output and adjust for any systematic effects. And there's an effort to try and do that in the laboratory as well. The laboratory tests tend to produce a lot more variability between samples than you see in the numerical models. Rocks that look very uniform turn out to have quite different properties sometimes, so it's harder to get that control in sample to sample comparison that you would get with a numerical model. So there's always more, you might call it aleatory variability in the outcomes. It's due to different materials that look almost the same, but the fine details of their makeup have a big effect on the mechanical properties.
Yeah.
And the specific form of the localization, and and actually in some experiments we've seen very obvious conjugate shear bands, and then one of them dies and the other one keeps going. This is inferred from acoustic emission monitoring. But so these kind of subtle, whether it goes one way or the other, is probably some subtle tiny detail in the process that you might not be able to observe even. So these are nonlinear effects. It's like the nucleation of a snowflake. It depends on some random thing, and then the whole shape of the snowflake is determined after that. So the nucleation controls what happens, and it may be similar, although it's much less sort of variability in the outcome for the faults. That once the shear band nucleates, it seems to determine what is going to happen in the eventual kind of fault when it grows.
Yeah. Edgar Hernandez is asking if you have studied the effect of rock heterogeneity, which kind of links a bit with a question I would have is, like, are there plans for further measurements?
Yes, we'll be developing proposals to extend this. We did look at rock heterogeneity with the granite tests because we had a pristine intact sample, and then we put some cracks in it for, deliberately putting in heterogeneity. And we saw significant differences, like I showed. Not least the fact that heterogeneity tends to make the crack growth smoother. So all of your statistics are smoother. So once it's an odd thing, but once you put in disorder, it kind of makes the evolution of the number of acoustic emissions per second or whatever, or the damage per second, much smoother. So the intact samples with low heterogeneity are much more brittle in a sense than once you've got damage in the material or porosity, then it's a kind of more sort of smooth evolution towards a failure. It's less affected by sort of jumps because you're blunted. A crack can only grow if there's another crack present. It's going to be blunt. The growth of the first crack is going to be blunted by one that it encounters, or if it grows into a pore or something like that. So the heterogeneity definitely helps to keep the system more stable.
Interesting.
As well as affecting the other mechanical properties. But that's the main difference that you can back out from what I showed today.
Right. Marcia Bohn is asking, you're using small samples. How can your result be upscaled to larger scales?
That's obviously a very big question. Some things probably do scale very well. The geometrical properties in the processes, you can go to fault zones in the field and you can see evidence for this kind of these kind of structures in the field. The power law distribution is not scale dependent, for example. The exponent might be different, it's possibly, and so on. We're not looking at fluids yet, the effect of fluids. So there's all sorts of reasons that think that things might be different on a bigger scale. I'm not one of those who think that just because something happens in the lab, it's definitely going to happen in the earth. The structures seem to be very similar, but we see a lot of precursors to failure in the lab. We're generally dealing with very high strain rates, though. So one of the biggest scaling issues, I think, based on the debate on earthquake precursors, for example, is the fact that when you do a test very slowly, slower and slower and slower, creep test or something like that, you gradually see the precursor disappear. So these precursory signals we've been seeing, when you do the test very, very slowly, you've also got the possibility of compaction, pressure solution creep, thermally activated processes, which destroy dilatancy. So these dilatancy related precursors kind of disappear at a strain rate as you approach, the deformation rate of the Earth around an earthquake zone. So one of the reasons we might not have such reliable precursors, there's lots of candidate precursors and people have observed things happening, but there's no smoking gun on precursors to natural seismicity, anything like we see almost every time in the lab. So something changes between the lab and the field, and the main candidate is the strain rate and the associated chemical reactions, fluid flow, anything with a time dependence, which serves to accommodate the same deformation without producing so much dilatancy. We've got satellite measurements now from INSAR and so on around earthquake faults, and the biggest signal is the earthquake. And then we see a strain relaxation in these data during the aftershock sequence, but we don't often see very much that can be detected with current instrumentation before that in the vast majority of cases. So So there is a big issue of scaling, and I wouldn't want to over-emphasize the potential, you know, and for improving understanding in that sense. It's possible, but I think mostly this is about trying to understand the physics and the origin of some of the structures that we see in the field. That seems to be quite a strong conclusion, I think.
Yeah, I said. David Brun is having a question. So obviously liked your talk and especially the conclusions on the control of seismic events. So what do you recommend as a control procedure for induced seismic events in subsurface operations?
I'm not sure I'm recommending anything. I think that's for the regulator to decide. But I do know that you know, that there have been successful programs on managing the risk of induced seismicity in coal mines based on event rate. So there is a precedent in the South Wales coal field. Peter Stiles many years ago set up an operation to monitor mining-induced seismicity. And, you know, when they got above about 100, this is my understanding, it may or may not be completely accurate, but when they got above about 100 events per day, they evacuated the mine, and they didn't go back in until the seismicity had decreased a threshold. So that's an example of successful management of risk, which was not required by the regulator. I think it was an experiment to see if they could you know, help the managers of the mine manage the risk. So there is a precedent. It's not just that our lab tests and will they scale, which is another question as we just heard. But it's worth thinking about, I think.
Yeah. So there's a few more questions by Milad Nadalo. So while asking if the non-self similarity of crack growth is for all the crack growth stages, since acoustic emissions event obtained from the final shear plane can show self-similarity.
Yeah. I mean, the scale and this, you know, the self-similarity of acoustic emissions, constant stress drop has been shown now across about 15 orders of magnitude or something like that. It's really phenomenal. It's almost as broad a bandwidth as the fractal objects you get in a cloud. So it really is, the source mechanics of the acoustic emissions are very scale invariant. But when you're measuring a crack, what you've got is the result of many intermittent growth episodes in the crack. So, and it's these intermittent jumps that produce the acoustic emissions. So there's not a one-to-one correlation between the cracks that you see and the acoustic emissions that you would measure, because it's an incremental change and it's dynamic. But yeah, as far as we can tell, with fluctuation, you know, with a large fluctuation, there's a larger random component as well. The power law scaling works on all scales pretty much, in, you know, between the lab and the field, and the stress drop from acoustic or seismic events is pretty constant. So it really is scale invariant. But that is a good question. Is that if that's true, and I believe it is with the evidence we've got, then it does beg the question of how is that related to these changes in the aspect ratio of the cracks that we see in these tests.
Andreas, you muted yourself. Would you unmute? We did not hear.
So I had to ask the dog to order. So he's defending the house again. So can we say that the final shear plane growth shows self-similarity, which is a follow-up question by Milad?
It probably does if you define the strain as the amount of shear divided by the length of the, you know, the zone with relatively high shear. That probably is self-similar growth, though we haven't checked that. In terms of the width of the deformation band, no. The width stays pretty constant. It doesn't grow that much. In these tests anyway. There is evidence in the field, though, that the growth of faults in the field by repeated earthquakes produces scale invariant growth. Patience Cowie showed that a long time ago, both with field observations and with numerical simulations. Remarkably scale invariant growth. So the damage zone widens as the fault grows, and that was a surprise. That's not exactly something that we see here. Now, it might be something to do with having a small sample and the effect of the boundary being very close to the fault. But that is a good question. It's not consistent with what we see in the field. The fact that we just have a sharp shear band and not that much deformation outside. We definitely see more damage zones in bigger samples in the lab. So we see more evidence of something approaching that, when we get up to a few centimeters, up to 10 centimeters diameter cylinders. So there may be an issue there, actually. There's some critical sample size to grain size ratio where you see that effect.
Yeah, there's a third question from Milad asking how you differentiate between aseismic and seismic events.
Okay, so we don't distinguish between events. What we know is the total seismic moment. So you add up, so you have a magnitude, you take 10 to the power 3.5 times the magnitude or something, and that gives you the seismic moment, which is a measure of the product of the area of the source times the slip times the shear modulus. And you add them all up and you get a number. And then you can calculate the total seismic moment you'd expect from the deformation using a formula by a Russian mathematician geophysicist called Kostrov, Volodya Kostrov, and that gives you the total strain. So you divide one by the other and you get the proportion of seismic events. So you don't actually count the aseismic strain. You do that calculation by comparing seismic to total strain. Yeah.
Good. And the last question is by Amir Saman Rezayan.
Yeah, we are running out of time, so that would be the very last.
It's the very last. So he understands rock mechanics studies are used to relate to induced seismicity, for instance. But if applicable, how are they to anticipate rather than to prevent natural catastrophic failure?
That's a good question, and obviously that's the holy grail. Like we would all really like to be able to do that. Service on the Commission for Earthquake Forecasting and so on. We looked at a lot of evidence in the literature for the systematic existence and reliability of precursors, and the jury is still very much out on that. It's a pity, because if the Earth behaved like our lab tests, it would make our job of anticipating events much, much easier. So maybe they really are unpredictable, and there isn't anything we could do, and we should really just concentrate on mitigating the risk, not predicting the events, but accepting they're going to happen anyway, and getting the buildings and the infrastructure right, and so on. And that's proven to be the best way to respond to the threat of earthquakes. It's a kind of known. Engineers may disagree about the best way to do it, but that there are pretty good norms for how you build buildings to withstand earthquakes now. And there's lots you can do without being able to predict earthquakes. And even if you could, what would you do if you had to evacuate, a city with 10 million inhabitants, with 3 days' notice, or 1 day's notice, or an hour's notice? It's not clear that would actually be something you might want to, sort of do in the balance of risk. What would happen if you suddenly had a whole city trying to evacuate all at once? So there's a lot of debate about this, and there's some good books on it by Susan Hoch's book is a very good one on the history of earthquake prediction and the kind of search for precursors and the debate that came around that. But the Earth is a pretty noisy place, and it's very easy to see fluctuations before earthquakes if you look after the fact. You know, so the problem is identifying these things in real time. You know, when I started out, people were writing papers about precursors, and the practice was you waited till there was an earthquake, then you had a look at the geophysical data, and where there was a fluctuation, you would publish that, and where there wasn't, it would just be left aside, you know. So there wasn't a proper systematic study of these, and what we had was a very selective literature, and often quite noisy signals were interpreted as having some significance because of the implications. You know, if you could have found them, it would have been, you know, sort of completely transformative. But people are just much more skeptical now, on average, on whether they might or might not exist, and we can think of good theories for why they might not exist, or why they might exist, as we see in these lab tests, but they're on such a tiny scale we wouldn't see them with current instrumentation. You know, there certainly isn't the widespread dilatancy that people were looking for in the 70s and the 80s. It doesn't seem to exist in the sense that people thought at the time there. Now that we've got the satellite data, we can observe the dilatancy directly.
Okay. So thank you very much, Jan and Andreas also, and thank you to the audience. We could have run this session, I guess, for another hour, but I believe our speaker also needs to take rest a bit, as well as Andreas, who is busy with teaching in this period. Thanks a lot to everybody for the lively discussion session. You know how to find the speaker with the email address and conferences, hopefully soon to be happening in person. We all hope for this. So I'd like to also take the chance and introduce our next week's speaker. Next week, we are going to host Auke Barnhorn, who actually posted questions also here today as well from TU Delft. Auke will speak also from a laboratory perspective about the matter of rock failure and seismicity. So until next week, 3rd of February, stay happy, healthy first, and then tuned into this channel for another geoscientific and geoenergetic lecture. Jan, I see a lot of compliments, a lot of thank you and great talk,
okay, thank you.
etc.
No,
so it was
thank you for listening, and it was great questions. You know, lots still to do.
Yeah, plenty of them are just thanking you for all the elaborative also responses that you also gave to the questions. Thanks a lot. Have a nice evening, everyone. Bye-bye.
Okay, you too.